I think I've done something unique with this circuit. I've scoured the internet for anything with comparable features and haven't found a single thing like it. Before I get into the details of what this circuit does, I should probably explain the work that led up to it.
Many years ago, I received a Roboraptor as a Christmas present. As cheap stuff typically does, it eventually broke and I couldn't fix it. But rather than just throw it out, I figured I could work my robotics wizardry on it to make it even better than it was.
Originally, the Roboraptor ran off of 6 AA batteries, 2 batteries providing 3 volts for the logic circuits, and 4 providing 6 volts for the motors. I really don't like split power supplies like this, because some of the batteries end up dying first, because they're putting out more current, and they're also not rechargeable in situ. Instead of that mess, I figured I could just power the whole thing off of a large lithium battery. Not this one, of course, it's way too small.
The battery I'm planning to get is only one cell, or 3.7 volts, so the motors won't be able to spin very fast on that voltage. As a result, I found myself in need of a step-up module. I figured it would be a good exercise to build it myself, and anyway, none of the mass-produced modules I found online had any sort of software-adjustable output voltage.
The result is this circuit. I do know that breadboards are a bit hard to follow, so I drew out the circuit here. It's a pretty standard circuit for a boost converter, nothing new, but for good reason, it works. The controller chip pulse width modulates this transistor, which causes the magnetic field in the inductor to build up when the transistor is on, and when the transistor is off, it releases that energy in the form of a higher voltage through this diode into the output capacitor. The inductor doesn't create more energy, it just trades high current and low voltage for high voltage and low current. Exact math is a little wonky and involves calculus, but the Wikipedia article on boost converters has a good analysis. That link is in the description. The key thing is that the output voltage depends a lot on the actual output load current, so the best solution to keep the voltage stable, and the method that all boost converters, including this one, use, is to just monitor the output voltage and adjust the duty cycle with some sort of control loop. This resistor divider feeds the output voltage back to an analog pin on the controller, so it can adjust the duty cycle to keep the voltage the same as the current demands of the load change. The innovative part about this design, as far as I can tell, is the chip that's doing the work of controlling the circuit. It's not a dedicated boost converter chip, it's actually a microcontroller, the ATtiny85 to be precise. This does have some trade-offs. The maximum switching frequency I can get is about 32 kilohertz, which requires a much larger inductor and capacitor as opposed to the 200 kilohertz or even 2 megahertz of commercial controller chips, where the inductors are almost flat as the chip itself. However, the one big benefit that I cannot go without by using the microcontroller is that this has a built-in I2C peripheral, which allows the microcontroller to talk to the host and change voltage dynamically in real time, as the host microcontroller commands it to. I've added a motor as a load and a voltmeter to the output of the circuit so you can kind of see what's going on. Here the motor is connected directly to the supply voltage, which is about 3.3 volts. Now the motor is connected to the output of the boost converter, but the converter is shut down, so that the output voltage is just the same 3.3 volts minus the diode drop, or about 2.6 volts. This black jumper wire is tied to the reset pin on the ATtiny85, and I have the code set to start at about 6 volts, so watch what happens when I unplug it. And there you go, 6 volts out from 3.3 volts in. Now, that's just a normal boost converter, but this one has a special feature, as I mentioned earlier. Over here, this microcontroller is able to communicate with the ATtiny85 over the I2C bus. It's an ESP32 in this case, but it just has to be something with an I2C master peripheral. This is the Arduino serial monitor, which is connected to the ESP32. I'm going to send a command to tell the ATtiny85 to increase the voltage to 9 volts. And you can hear the motor speed has increased, and the voltmeter is now reading, I guess 9 volts. It's fritzing out a bit more than it usually does, I'm not sure why. Now I'm going to set the voltage to 3.9 volts, so it should be just about the same as without the boost. Now I'm going to try to set the voltage to 1 volt and see what happens. As you can see, the meter isn't reading anywhere close to 1 volt, and it's stopped fritzing out because the converter has completely turned off, because all it can do is increase the voltage. Since 1 volt is less than the input 3.3 volts, it can't increase it, so it just shuts off. So, there you have it. As far as I can tell, it's the world's first software-adjustable boost converter. The software running on the ATtiny85 is available on GitHub, as well as a copy of the circuit diagram if you would like to build it yourself. The link for that is in the description. If you found this video informative, feel free to hit that like button down below. And if you're interested in seeing more of this electronic stuff, you can subscribe to my channel. This video was a lot of work, so thank you for watching. See you in the next one.